So now we'll do one more example with a checkerboard, a 3x3 checkerboard. Let's say we have four blue tiles and 5 green tiles. And so we have the dihedral group of a square. Let's just call it, this is P, this is Q, this is R, this is S for the diagonals. So we have reflections across the corresponding diagonals, and then we have rotations, identity, I'll just call it 90, 180, and 270. Like we did before, we'll act on the checkerboard with each symmetry. So if we're reflecting over R, 1 goes to 9 and 9 goes to 1, 2 goes to 6, 6 goes to 2, 4 goes to 8, 8 goes to 4, and then 3, 5, and 7 are all related to themselves. S is the same structure. 4 go to 2, 7 goes to 3, 8 goes to 6, and then the remaining 3 are in their own cycle. And we're actually going to get the same structure for each of the reflections. 1 to 7, 7 to 1, 2 and 8, 3 and 9, and then 4, 5, 6. And I'll fill in the rest and skip to 90 degrees for a demonstration. We would have 1 goes to 3, and 3 goes to 9, 9 goes to 7, and 7 goes to 1. Then we have, this is a clockwise rotation, by the way, 4 goes to 2, 2 goes to 6, 6 goes to 8, 8 goes to 4, and then 5 stays by itself. This is going to be the same structure for the cycle monomial for 270 degrees of 2 cycles of length 4 and 1 cycle length 1, because 270 is just 90 in the opposite direction. And for 180, I just pasted what it would look like. I don't know if this is helpful, but we can see that the cycle notation would be 1 goes to 9, 9 goes to 1, 3 goes to 7, 7 goes to 3, 4 goes to 6, 6 goes to 4, 2 and 8 are paired, and then 5 is by itself. And just for the other cycle notations, I'll just fill in. We have 1 and 3, 4 and 6, 7 and 9, 2, 5, 8. Everything's related to itself, and then again we have 2 cycles of length 4 and 1 cycle of length 1. I started already alluding to it. We have the cycle monomials. I just filled those in, and we can now make the cycle indicator. So we have 1 over 8, so that's the size of our group, times we have 4 cases of z2 to the third times z1 to the third, plus 1 case of z1 to the ninth, plus 2 cases of z4 squared times z1, and then 1 case of z2 to the 4th times z1. And that should be equal to 8, and it is. For the sake of time, I paused the video and wrote out the weighted enumerator and just plugging in b plus g. So I originally said we had 4 blue and 5 green, but I meant to just say we had blue and green squares. And I want to consider now actually how many distinct ways can we color the checkerboard with 6 blue tiles and 3 green tiles. Just wrote them out to save time, and considering the first one, how many ways can we get 6 blue tiles and 3 green? So there are 2 different ways we could do this. since the green has a power of 3, it can either be that we take one of these and get g squared, and then we'd have to take one of these and get g, or we could do all 3 g from here. So if we do that second option, all 3 g from here, then there's only one way to do that, and then this leaves all of b to the 6th from the left side. So that's one way. And then plus, we could do choosing one of these to give us g squared. So that would be 3 choose 1. And then times one of these to give us g, 3 choose 1. And then the remaining 2 b's, whichever they are, or whichever 2 give us the b's, they'll just fall into place. So that's 1 plus 3 times 3 equals 10. For the next one, since they're all to the first power, we can just do 9 choose 6 to choose the 6 b's, and then the rest are just automatically green. So that one's just 9 choose 6, which is equal to 9 choose 3 if we decided to focus on the green. This one, we've already exceeded how many greens we're allowing. So this one's 0. We can't get b to the 6 times g cubed. And then this one, since g is odd, we would have to choose one g from here, and then that leaves us with finding g squared left. And there are 4 choose 2 ways to pick g squared. Actually, 4 choose 1. We just want to choose one more g squared, and then the remaining 3 are our b squared, and there's 3 of those, so that gets us to b to the 6. So this is just 4 ways. Now we just plug it back into our formula for our weighted numerator. In numerator, we have 1 over 8 times, can't forget the 4, which I almost forgot before. So it's 4 times 10 plus 9 choose 6 plus 0. 2 times 0 is 0 still, plus 4. And that is equal to 40 plus, I calculated this on the side, is 84 plus 4. So this is 128 divided by 8 is 16. So there are 16 distinct ways to color a checkerboard, a 3x3 checkerboard, with 6 blue and 3 green tiles. And here are the 16 distinct checkerboards. Anything not seen here can be obtained by rotating or reflecting one of these. And that is how we use Polya's theory of counting to find distinct colorings. It relies on our familiarity with group action and the dihedral groups of symmetries. Once we find the orbits, it's just a matter of counting. Thank you for watching my video, and I hope you enjoyed it.